All right, stat students, here we are, section 7.2. Just got a few more sections left to go in our course this year, so we are on the downhill side of the curve here, right? So this was uphill, we got to spring break, and now we're on the downhill side. We're way over here. So congratulations. 7.2, we're going to be looking at the applications of the normal distribution, and we're going to be looking at some standardizing things, and this section is going to be a little bit mentally challenging just because there's going to be some new notations and things that you have to look at. But we want to find and interpret the area under a normal curve. We've also, looking back at from section 7.1, we know that there's two applications of that area under the normal curve. And those two applications are the area under the normal curve shows the proportion of the population that would have the characteristic or trait of that whatever random variable we're looking at. And the other one is the probability that a person chosen at random from the population would have that characteristic is also equal to the area under the curve. So we're going to be doing more of that in this section. And we're also going to find the value of a normal random variable. So what that means is given the area under the curve or given certain characteristics, what is the raw score that corresponds to that. So that's kind of working in reverse of what we're going to do, what we've done so far, and what we're going to do during this first objective today. So finding and interpreting the area under a normal curve is going to involve, first of all, getting a new definition. We want to talk here about standardizing a normal random variable. Now, anytime you standardize something, that just means we want to create one way to talk about it so that it all makes sense, regardless of what the random variable is. We're talking about one standard deviation above the mean. We can standardize that, and the truths of the empirical formula apply to whatever normal distribution we're talking about. So we can come up with a standard score or a standard number that applies to it, and that's great. So suppose that the random variable x is normally distributed with a mean of mu and a standard deviation of sigma. Then the random variable z is equal to x minus mu divided by sigma. Now, let's talk about what this means. Okay, suppose that a random variable x, let's put this in context. Suppose that a random variable x is IQ. We've just been using that one enough, and it's just we're familiar with it. The numbers are easy to work with. Suppose that IQ is normally distributed with a mean of 100 and a standard deviation of 15. That's the numbers that work there. Then the random variable z equals x minus mu divided by sigma. Okay, so x is, let's just say our IQ score is 125. Now let's make it easier than that. Let's make it 130. Okay, so our z score for a raw x score of 130 is going to be 130 minus the mean, right, divided by the standard deviation. And so this z score would be 2. So an IQ score of 130 is going to be a z score of 2. All right? And that means it is 2 standard deviations above the mean, right? 130 is 2 standard deviations above the mean. It's mu plus 2 sigma, okay? So that's what we get with 130 score. So we're just converting a raw score, right? 130 is our raw score. We're converting that raw score to a standardized z-score of 2. Because if it's 2 standard deviations above the mean, and we know a whole lot about that raw score, and we can have a table, and we'll look at a table here in a little bit that's going to do that. So let me see, did I miss anything at the bottom? Z is also normally distributed with a mean of 0 and a standard deviation of 1. the random variable z is said to have a standard normal distribution. So when we standardize this variable, in other words, when we convert raw scores to z-scores, the resulting distribution is still normal. That's what the bottom part of this definition is telling us. It's normal with a mean of 0 and a standard deviation of 1. Okay, so let's look at what this looks like. So z, I really don't like this capital Z down here. That's the curve, right? Little z is our z-score. So every value along here has a z-score. So this might be 0.3, and this might be 1.25. This z-score might be negative 2. So the lowercase z is the little z-score along the bottom, and then our capital Z is our random variable that represents the curve. So the z is normally distributed, and that's what the curve is going to look like. So what we just have is a standardized normal curve with the standard deviation again at this inflection point is 1 standard deviation. It's 1 above the mean, and it's actually 1. So 1 standard deviation above is 1, 2 standard deviations above is 2, so on and so forth. It standardizes the way we look at raw scores. Okay, now the table gives the area under the standard normal curve for values to the left of a specified z-score. Now the table that this is talking about here, this table is Appendix A, 11, and 12 in your textbook. Okay, A11 and A12 in your textbook. And there's also a picture of this table, or at least part of it, on in the Chapter 7 documents folder in PowerSchool Learning. So A11 and A12 is talking about the table. The table of values gives the area under the standard normal curve for values to the left, that's important, of the specified z-score as shown in the figure. So if, I don't know what this z-score is, maybe this z-score is, I don't know, it looks maybe a little to the left of the inflection point, or maybe it's right at the inflection point. Let's say it's z equals negative 1.1. Okay, the table of values that you look up in the back is going to give you the area to the left of that. So that table we're going to use to help determine the areas, because again, going back to 7.1, that area translates to probability that an individual will be in that region. It also shows the proportion of the population that is going to be in that region. So the area under the curve is becomes the probability and becomes the part of the population that's going to fall into that region. So IQ scores can be modeled by a normal distribution of 100, and mu equals 100 and standard deviation of 15. An individual whose I score is 120, okay, is 1.33 standard deviations above the mean, okay? 1.33 standard deviations above the mean. And we get that just by converting our raw score, right? Here's our raw score of 120, and that raw score converts to a z-score of 1.33. It's 1.33 standard deviations to the right of the mean. It's positive, so it's to the right. If it's less than the mean, if this value, if our raw score is less than the mean, then we're going to get a negative value, and that means it's to the left of the center. So what does that mean? How can we use the table to look at what that means? So if you go to the table, this part of the table is on A12. 1.33, here's the tree, or the stem, and the leaves are up here. So 1.33 has a area of 0.9082. Okay, here's what that means. The area to the left of 1.33 standard deviations is 0.9082. It means that 90.82% of the population has an IQ that is less than or equal to 120. Okay, that's how we can interpret this score. 90.82% of the population has an IQ less than or equal to 120. Okay, and this table is going to be very, 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 very helpful to us moving forward. Now, if we wanted to look at that on a standard normal curve, we can do that. Let me pull up a blank sheet of paper here. I wish I had a nice normal curve because you guys know my sketching is really bad. See, I already started off bad. If we start our normal curve, looks like this. It probably would be a little squattier than that because of our I don't need that axis. I need a horizontal axis. Okay, and this is IQ, so the mean here in the middle is 0 for a Z-score. The inflection point, again, I'm butchering this, the inflection point somewhere around there would be 1. And so 1.33 is going to be somewhere right in here. 1.33 is the raw score that we're looking at. And the area under the curve to the left of 1.33 standard deviations is, the area is equal to 0.9082, I think it was. That means 90.82% of the population, and this was a raw score of 120. Right, so if we're looking at raw scores, this is 100, one standard deviation above would be 115. So what we've done is standardize our raw scores into Z-scores, and then we do that so we can go to that table. We don't have to make a table for every single random variable. We can standardize it and use one table to get all of the areas and probabilities that we need to from that. So the calculator also has a feature that we'll look at some point that'll do this for you, but I want you to get used to using the table for a minute. Okay. Now we're also going to be using the complement rule. Okay, if the area to the left of 1.33 standard deviations or 120 raw score, if that area is 0.9082, then the area that's greater than that, because the areas have to add up to be 1, is going to be 0.0918. So 90.82% of the population has an IQ less than or equal to 120, and 9.18% of the population has an IQ that is higher than or equal to 120. So that's how this is going to work. All right, and these are also the same as percentile scores that we looked at earlier in the lesson. So this is how they convert a raw score like an SAT score or an ACT score into a percentile score as well. They standardize it and look at the percentages of the population that scored there. So this is gives us, again, this is our good old friendly standard normal curve empirical formula. So we have approximately 68% of the population that lies within one standard deviation of the mean, right? And then we add these other two values here. We're up to 95% that lie within 2 standard deviations of the mean, and so on and so forth. This one gives us a little bit more detail, but this is just showing the distributions for a standardized Z-score. Okay, that's review. Let's look at this. Find the area under the standard normal curve that is to the left of Z equals negative 0.38. Okay, because we're talking about the area or under the curve that's to the left. This is just a value that's going to come straight out of our table of values. So negative. This is going to be the first page of your distribution sheet, which is on A11. So negative 0.38. We're going to use negative 0.3 as our stem, and then the leaf is 8. So 35.2% of the people, or the area, is equal to 0.352 is what we would get there for that. Okay. Now, what's the interpretation of that? Well, 35.2% of the population is to the left of that Z-score, and the complement of that would be, 648, maybe 0.648. 64.8% of the population is to the right of that Z-score. So we're talking about complements there as we move forward. So the area under the normal curve to the right of z naught, of any z-score, okay, any z-score, the area to the right of a value, or the area that is greater than or equal to, is equal to 1 minus the area to the left. And the reason that's important is because our table of values, right, our table of values is what's going to give us this area to the left. This is the most common mistake that people make on the Chapter 7 tests and quizzes, that they misinterpret that value that they get from the table. Okay, so this is the area to the right is 1 minus the area to the left. That's an important rule for you to remember. Okay, so finding the area under the standard normal curve that is to the right. Okay, to the right, to the right. So if we're going to be to the right of z equals 1.25, that's equal to 1 minus the area to the left of z equals 1.25. Okay, so we would go to our table of values again, find the area that is to the left of 1.2. There's 1.2, and there's 5. So 0.894. The area to the right of that is 1 minus the area to the left, so that's 1 minus 0.8944, which is equal to 0.1056. All right, and that means that 10.56% of the population is more than 1.2 standard deviations away from the mean to the right of that, or greater than 1.2 standard deviations of the mean. And if we wanted to talk about IQs or whatever, this is going to work. All right, so here's some strategies. These three little slides are confusing because they're giving you strategies. These aren't actual problems that we're working. Okay, so if you are tasked with the problem of finding the area to the left, here's what it looks like graphically, right? There's the graph that we want to use. The way you do it is you convert your raw score to a z-score using that z equals x minus mu divided by sigma, okay? And then go to the table, find the row and column that corresponds to that z-score, and the area is going to be where they intersect. Okay, and another way you can do it is to use a calculator to find the area that's to the left. And we'll talk about that later, but the table's really easy to use. You'll have it available to you, so using the table is just really about as quick. Okay, so the strategy of finding the area to the right of an x value, if we're looking for the area to the right, okay, this is what it looks like graphically. We're looking for that area right there to the right. And that's equal to 1 minus the area to the left. So again, we would convert the x to a z-score, and then use the table to find the area to the left, and the area to the right is 1 minus the area to the left of z. So this, again, just the strategy. If you're told to find the area to the right of a value, that's how you do it. Okay. Now, the most difficult thing here is this one. If you want to find the area between two x values, okay? If it's not a straight up empirical rule, where you can go and find the tables, this is the process that you are going to use. You're going to have to convert both values to z-scores, okay? So you'll have a z1 and a z2. The area between z1 and z2 is found by taking the area to the left of z2 and subtracting the area to the left of z1. So let's look at that. Let's look at what we're talking about here. If we convert these x values to z values, z1 and z2, right? The area to the left of z2 is all of this, right? So we take all that area, and then to get that original shaded area, we would have to subtract back this area that's to the left of z1, and then that just leaves us the area between the two values. Okay, let me illustrate that again. It says that you take the area to the left of z2, right, and subtract the area to the left of z1. So if we take all of this area to the left of Z2, keeps on going, right? But we got extra there. We have to subtract out this little bit of area that's to the left of Z1 and to get the area that's just between the two values. All right, so that's how you would find the area between the two z-scores. All right, now let's look at an example of that. Find the area under the standard normal curve between, and here they're giving us z values, which is great. They could have given us x values and distribution information that we have to convert to z-scores. But find the area under the standard normal curve between these two things. Now, if we wanted to look about what that looked like graphically, it can give us an idea, right? So if we take this standard normal curve, that's not too bad, and we take a z-score of -1. So -1 is going to be somewhere right in here. And 2.94 is way up here, right? Because here's my mean. It's almost 3 standard deviations above the mean. That's a really high score. Okay, we would expect that area to be pretty large, right? So just kind of intuitively, because we know that from -1 to +1, +1 we got 68% right there, and this 50% to the right of the mean, 50% to the right of the mean, there's 34% right there, and you've got 16% over here. So there's a lot of ways. So you got 34, 16. And so there's a lot. We should expect this area to be quite large. So let's look at the process for doing this. We're going to find Z1 and Z2. The area between -1.02 and 2.94 is the area to the left of our larger value minus the area to the left of our smaller value. And from the table of values, that would be 0.9984 minus 0.1539, which gives us a total area of 0.8445. This is a pretty large area, right? That's how that would work. Now, what you need to do right now, what I would suggest you do is kind of make sure that you understand this example, and make sure if you have to pause the video and make sure that you know how to find those values from the table like we did the previous ones that we're looking at. Now, let's reverse it. Find the value of a normal random variable. Procedure for finding the value of a normal random variable is to draw the normal curve. It's always good to see a picture, right? Shade the area corresponding to the proportion, probability, or percentile that's given, and then use table 5 to find a z-score that corresponds to the shaded area. And then you could obtain a normal value from the formula by using x equals mu plus whatever your z-score is times sigma, sorry. Okay, and all that's doing, guys, is taking, if we're going from a z-score back to a raw score, so we take the z-score formula, z equals x minus mu, butchered it, x minus mu over sigma. If we cross multiply there, we get z times sigma equals x minus mu. And then if we add mu to both sides, we get mu plus z times sigma equals our raw score. So this is just the way you go backwards to do it. So let's put it all into practice, and I think this will make sense. The combined verbal plus quantitative reasoning score on a GRE is normally distributed with a mean of 1049 and a standard deviation of 189. What is the raw score? Now, if it's asking you for the score, what is the raw score of a student whose percentile rank is at the 85th percentile? So what we're looking for is some value here, right? Some value on this curve such that, and it's going to be somewhere over here, such that the area to the left is 85%. Now, where can we find values to the left of a z-score? Right? We're going to go to our table, and instead of looking for the percentile, we're already given the percent. The percentile is the 85th percentile. So if we look at our table of values, gosh, I didn't mean to do that. If you look at your table of values, what we're looking for is 0.85 in the table. So look for 0.85 in your table. 0.85. That's 0.085. It's going to definitely be on the right side. 0.85 is just a little less than 1.05. And they said it's 1.04. So that's how they approximated that to be 1.04. So to convert that back to a raw score, you get 1.04 times 189 plus the mean, which is a raw score of 1,246. So a person who scores 1,246 on the GRE would rank in the 85th percentile. Now, you definitely would not want to use 1.05 because that's greater than the value. So 1.04 is a good estimate there. All right, so let's see how they got exactly that value. Oh, actually, they did. Yeah, it was 0.8508. So 1.04. It wasn't 1.05. That was a mistake on my part. So 1.04 is the value you should have used. All right, let's go on. It is known that the length of a certain steel rod is normally distributed with a mean of 100 centimeters and a standard deviation of 0.45. Suppose that the manufacturer wants to accept 90% of all rods manufactured. Determine the length of rods that make up the middle 90%. Now this one's a little different, right? We want the middle 90%. We don't want values that are less than it. So what we want is we want values that would be, if our mean is here at 100, we want 90% right here in the middle, right? How much percentage would that leave on each wing, right? That would leave 5% over here, 5% over here. So this value right here, okay, this value right here is the value at which 95% would be to the left. Now think about that for a second. If we want the middle 90%, that means there's 5% left over on the left and 5% left over on the right. So this value that we're looking at here, whatever this raw score is, we've got to come up with that raw score. 95% of the total rods are to the left of that. So if you go to your table of values again, we're looking for this time 0.95. And you look inside the table until you find 0.95, and it looks like it's, you know, kind of dead between 1.64 and 1.65, 1.64 and 1.65, right in the middle of that. So the z value you would get on the right side is right between them. Z equals 1.645, and because it's symmetric, right? We've got 1.645 on this side. That means negative 1.645 would be over here. And to convert those raw scores to z-scores, we use the formula, the mean plus z1 times that. So our left-hand endpoint is going to be 99.26 centimeters, and the right-hand endpoint is 100.74 centimeters. So if they're going to take 90% of the rods, the length of rods that make up the middle 90% of all steel rods manufactured will be between 99.26 centimeters and 100.74 centimeters. So that's kind of the most difficult problems that you'll look at in this section. So make sure that you understand the concept of the symmetry and these areas on the outside, and the area to the left of this upper value here, the area to the left is 0.95. So we can get that z-score out of the table This z-score can come from the table by looking for 0.195, and that value is 0.1645. Now, you could also find the left-hand z-value for that matter. The area that's to the left over here is 0.05, and if you look at your table of values on A11, if you take a minute to look at A11, and I encourage you to do this because this is the difficult part of this. On A11, if we're looking for 0.05, you're looking for 0.05 in the table. 0.05 is between 1.64 and 1.65, so that's 1.645 again. So you can get this z-value directly from the table by looking for area equals 0.05. So that may be even the easier way to do it, but whatever kind of makes sense to you works. Okay. So the notation Z alpha, pronounced Z sub alpha, is the Z-score such that the area under the standard normal curve is to the right of Z sub alpha. Okay, so that's just a notation that's given to us there. Z sub alpha is just some notation. Z-score such that the area under the standard normal curve is to the right of Z sub alpha. And that's going to be, again, 1 minus the area to the left. Okay, area to the left. Or no, I'm sorry. This is 1 minus the area that's to the left. So that's a concept that you'll have to use in your homework some. So this is your homework from 7.2. This is not going to be due until Monday night at midnight, so you'll have all day Monday to do this lesson. And then 7.2 will be introduced on Tuesday. Our last day for any new work is next Friday, and then the exam, whatever the exam is going to look like, it will be the following Monday. So I can assure you that it is not something that you need to worry about at this point. So have a great day. I hope to see you soon.